Chapter 7, Basic Instrumentation. This chapter reviews a few important basic technical elements regarding computers and outlines the equipment components of the CT scanner, including the imaging system, the CT computer and the processing system, image display, storage and recording, and communications, CT and PACS, and the CT control console and options and accessories for CT systems. The computer system consists of at least 3 elements: hardware, software, and computer users. Hardware refers to the physical components of the machine. Software refers to the instructions that make the hardware work to solve the problems. And people are the computer users because they design, develop, and also operate the hardware and the software. These elements results in 3 core characteristics that reflect usefulness of computers. These are speed, meaning can they solve problems quickly; reliability, so are they prone to errors? Remember, computers are only as good as the people who program them. And also storage and capability. Can they store a vast amount of data? A computer processes the data or information it receives from people or other computers and outputs the results in a form suitable to the needs of the user. This is a 3-step process, and it involves input, processing, and output. The organization of a computer includes at least 5 hardware components: the input device, central processing unit, internal memory, output device, and external memory or storage. Input hardware refers to input devices from which information can be sent to the computer, and an example of one of these input devices is a keyboard. Processing hardware includes the CPU and the memory. The CPU is the brain of the computer, and it consists of a control unit that directs the activities of the machine and an arithmetic logic unit to perform mathematical calculations and data comparisons. It also includes an internal memory or main memory for the permanent storage of software, instructions, and data. After data are processed, results are sent to an output device in the form of a hard or soft copy. An example of a hard copy output device is a printer. An example of a soft copy output device is when the results are displayed on the monitor for direct viewing. Then, processing results can be stored on an external storage device, such as a disk or a tape, and possibly even optical storage devices. Hardware receives its instructions from the software. The instructions are written in steps that specify ways to solve problems, and then these instructions are called programs. There are 3 categories of software. First, there's system software, which refers to programs that start up the computer and coordinate activities of all the hardware components in application software. And then there's application software, and these are programs developed by computer systems users to solve specific problems. And the third category is software development tools, which includes computer or programming languages. Computer architecture refers to the general structure of a computer and includes both the elements of hardware and software. Specifically, it refers to computer systems, computer chips, circuitry, and systems software. There are 2 types of CPU architectures: complex instruction set computing, CISC, and reduced instruction set computer architecture, RISC. CISC has a microprocessor design and has more built-in operations than the RISC microprocessor design. These architectures are capable of processing or operations such as serial or sequential processing, distributed processing, multiprocessing, multitasking, parallel processing, and pipelining. CT technologists should understand the meaning of these terms because they are used in CT literature and also in the manufacturer's brochures for the scanners. In serial or sequential processing, information is processed in order on which items are entered and stored in the computer. This is a very simple form because there is one instruction processed at a given time. In distributed processing, information is processed by several computers connected by a network. This requires a highly structured environment that allows hardware and software to communicate, share resources, and also to exchange information freely. Multitasking is when a computer works on more than one task at a time. Multiprocessing is when the computer uses two or more central processing units, and each CPU works on a different set of instructions, so they kind of tackle their own set of instructions per each CPU. It increases the speed or the computing power. There's parallel processing, which can only run on a computer with two or more processors running simultaneously. A number of processes can be carried out at the same time with parallel processing. Then there's pipelining. This is a method of fetching and decoding instructions in which, at any given time, several program instructions are in various stages of being fetched or decoded. Pipelining speeds the execution time by ensuring that the microprocessor doesn't have to wait for the instructions. When it completes an execution of one instruction, the next set of instructions is ready and waiting. Three major systems of the basic equipment configuration for CT are the imaging system, computer system, and image display, recording, storage, and communication system. The purpose of the imaging system is to produce X-rays, shape and filter the beam to pass through only a defined cross-section of the patient, detect and measure the radiation passing through the cross-section, and convert the transmitted photons to digital information. Major components of an imaging system are the X-ray tube and generator, which is responsible for X-ray production, calorimeters, which help define slice thickness and restrict the X-ray beam, the filter, which protects the patient from low-energy rays and ensures beam uniformity at the detectors, which capture X-ray photons and convert them into electric signals, and also detector electronics. A computer system includes an output device, CPUs, array processors, interface devices, back projector processors, storage devices, and communications hardware. And also, it includes software that allows each hardware component to perform the respective specific task. The software enables scanning procedures to be created and activated from an input device, and extensive image display and analysis functions. The third major system of the basic equipment configuration for CT is the image display, recording, storage, and communication system. The purpose of this system is to display the output digital image from the computer in a meaningful form to the viewer, so maybe the tech or the RAD. It also provides a hard copy of the image on a recording device that provides a permanent copy. It facilitates storage and retrieval of digital data to address problems of film storage and archiving. And it also communicates images, diagnostic reports, and patient demographic data in an electronic environment like a PACS or a RIS system. The imaging system is made of several units housed in the gantry that work together to acquire an image from the patient. The gantry and the patient table, also known as the couch, are often referred to as the scanner. The gantry is mounted framework that surrounds the patient in a vertical plane. It contains the rotating scan frame onto which the generator, tube, and other components are mounted, and it houses imaging components such as slip rings, tube, high voltage generator, calorimeters, detectors, and the DAS. X-ray tubes of slip ring scanners require high instantaneous power and also have larger anodes. The generator is usually a small solid-state high-frequency generator mounted on rotating scan frames. Since it's located close to the tube, only a short high-tension cable is required to couple the X-ray tube and the generator together. This is the design that eliminates large control cabinets and the long high-tension cables that the older scanners previously had. Power ratings to generators usually range from 30 to 60 kilowatts, depending on the scanner. Gantry cooling is crucial since ambient air affects several components. Now, the modern cooling systems circulate ambient air through the gantry. Two important features of the gantry aperture are that most scanners have a 70 centimeter aperture. The aperture just refers to the hole in the gantry. And that the second feature is that the gantry tilting range varies between usually plus or minus 12 to plus or minus 30 degrees. And it's usually in 0.5 degree increments. The patient table provides platform on which the patient lies during the exam. This consists of a tabletop which floats and rests on a pedestal. The tabletop is usually made of carbon fiber because carbon fiber is known to have low absorption and high strength, which in CT makes it useful for imaging the heavier patients. The pedestal houses the electrical components that facilitate vertical and horizontal couch movements. The vertical movements provide a range of heights to make it easy for the patients to get on and off the table. And this is especially useful when imaging the older patients, like the geriatric patients, trauma patients, and as well as pediatric patients. Horizontal or longitudinal movements enable the patient to be scanned from head to thighs or to feet without repositioning. An important component of computer processing architecture for CT and MRI is the array processor. This is a dedicated electronic circuit capable of the high-speed calculations in CT. They feature key elements such as speed, power, flexibility, and expandability. To accommodate these elements, the array processor architecture may consist of multiple dedicated processors and storage. This accommodates high-speed data acquisition and image reconstruction, storage, display, and recording. It also may include a dedicated image storage and independent manipulation of the data. And it could include the capability of DICOM network. DICOM is a standard connectivity in the radiology department. I'm sure many of you have already heard of this, if not, already know it in depth. DICOM allows multimodality and multi-vendor equipment to connect electronically to facilitate data and image communications within a department. Medical imaging and radiation therapy involve technologies that generate a large amount of data sets that are also made up of a large amount of similar elements. Processing these data sets quickly becomes an issue for the CPUs of modern computers today. The use of IR algorithms requires increased computational power even yet, and this is now possible with the use of the graphics processing unit, or the GPU. The GPU can be used to reduce the processing requirements of the CPU. A normal GPU uses parallel processing, which gives capability of fast mathematical processing. One of the main features of the architecture of the GPU is the graphics pipeline. This includes several graphics processors, also known as parallel processors, that can perform mathematically intensive operations. It decomposes graphics computation into a sequence of stages that explores both task parallelism and also data parallelism. Task parallelism is achieved when different tasks are performed simultaneously at different stages of the pipeline. And data parallelism is achieved when the same task is performed simultaneously on different data. All right, I know that there looks like there's a lot of information on this slide, which there is, but we'll get through it. I will break it down. The operator of the scanner must be able to communicate with the system to allow scanning. And this is usually done by a keyboard, commands typed in on a keyboard, or even a touch screen. The operator selects preset protocols, as well as they also select different algorithms. depending on the exam that they're performing. The PC interfaces that use a mouse and drop-down windows-based menus are commonly used as well. Operating systems are programs that control the hardware components and the overall the overall operation of the computer. They also allow the computer to run other programs. The operating system consists of a supervisor, which resides in the primary memory and controls all of the other portions of the operating system. The software systems of CT scanners have been evolving rapidly as more and more clinical applications are made possible by multi-slice scanners. CT software can be placed in one of three categories. There's reconstruction software, which builds up the image from raw data collected from the detectors. And reconstruction software consists of very sophisticated algorithms. There's pre-processing software, which performs corrections on the data collected from the detectors before the data are sent to the reconstruction computer. An example is beam hardening corrections. Then there is image post-processing software. This operates on reconstructed images displayed for viewing to facilitate diagnostic interpretation. This software can be placed in two categories: basic and advanced image visualization and analysis tools, which include MPRs, MIPS, and 3D shaded surface display reconstruction. On to display and storage for CT. Liquid crystal flat panel displays are quickly replacing cathode ray tube displays. Images are usually displayed in grayscale, however, there are some images displayed in color. The display system includes features such as the display matrix, the pixel size, bit depth, CT value scale, grayscale, image monitor and the number of lines, selectable window width and window center, and highlighting. All of these are specific to each manufacturer. For the storage part of CT, digital images are stored in 2D pixel arrays, and each pixel point is represented by a number of bits that determine how many gray levels can be represented by that particular pixel. The CT image size varies accordingly to which anatomy part is being examined, but a typical CT image has a matrix size of 512 by 512 by 8 bytes, which is 12 bits. Storage devices for CT include magnetic tape and discs, digital videotape, optical discs, and optical tape. The capability of the optical disc is much higher than that of magnetic tapes. The requirements for hard copy recording of CT images include broad grayscale contrast resolution to enable the perception of subtle differences in tissue contrast, and high-speed spatial resolution in order to detect boundaries of different tissues. Laser recording systems were used to meet these requirements. Laser cameras replaced the video camera technology, and there are two types of lasers used for film recording in CT, which are solid-state laser diodes and gas lasers. The gas lasers include helium neon, helium, cadmium, argon, carbon dioxide, and nitrogen. The helium neon is the simplest and the most reliable gas laser. Now on to image communications, which refers to electronic networking or connectivity by using a local area or wide area network. The local area network connects computers separated by short distances. Examples of this include the computers in the RAD department, and a wide area network connects computers separated by large distances, such as computers in another country. The internet is a great example of this. Connectivity ensures the transfer of data or images from multi-vendor and multimodality equipment according to the DICOM standard. CT scanners must support various network speeds, and these speeds are usually as fast as 10 100, and this is supposed to be 1,000 megabits per second. As you all know by now, the CT scanner is connected to PACS, and the essential components include the scanner, various interfaces, and a PACS controller, which the PACS controller includes a database or image server, the archive server, short and long-term archives, and the RIS or HIS system. It also includes the web server and image display, which are all connected by computer networks. The PACS is integrated with the RIS and HIS by communication protocol standards. There are two popular standards, and the first one that we'll discuss is the Health Level 7, and this is referred to as HL7. I'm sure you've heard of this before. It is the standard application protocol for use in most HIS and RIS systems. And then there is DICOM, and this standard was developed by the American College of Radiology and NEMA, which stands for the National Electrical Manufacturers Association. DICOM conformance is absolutely mandatory when dealing with a PACS. So once images are acquired and sent through the computer network, they are usually displayed for viewing and stored temporarily or permanently for viewing and analysis. Since the CT image files are so large, they place huge demands on storage requirements and also the speed of transmission over the network. So compression of the images is needed. Like we've said before, there are two types: lossless, which is the reversible form and no info is lost in the process, and then there is the lossy compression, which is irreversible and some info is lost in this process. So then there is interfacing with the PACS and the CT. The work lists are used to match cases from the CT scanner to various workstations. So a PACS must be capable of creating and using the work lists effectively. Image distribution is also absolutely crucial regarding PACS, since it must have the ability to send images to referring physicians. The CT Control Console allows the operator full control of the physical system, such as gantry control, and allows for real-time processing such as multiplanar reformatting, 3D manipulation, zoom, and pan. The integrated console controls the entire system and allows for operation of various functions. This includes the floating keyboard, touch panel, and the touch panel allows system parameters and control parameters to be carried out without typing on the keyboard. The integrated console also includes window controls, such as window width and window level, image display, such as the monitors, high-capacity optical disk drive and the CD writer, and the control functions, which the control functions include auto-archiving, auto-windowing, and auto-voice.